Hello, everybody. This is Miss Peachy from your WCA Physics A class. I'm looking here at Unit 6, Lesson 4, and we are still looking at momentum. We are going to mathematically kind of prove that momentum works here. So again, conservation of momentum in a closed system of two interacting objects, their total momentum will remain constant. Mass, as you know, is the amount of matter in an object. We measure that in kilograms generally, and velocity change in displacement over time. And we usually use meters per second as our kind of standard unit of measure there. But we are going to prove the conservation of momentum here. So essentially, when we look at conservation of momentum equations, we are going to be looking at collisions that occur. Now remember, we're trying to mitigate external forces. So oftentimes these are going to be examples of collisions that took place on ice, or collisions that took place between two objects in the air or in space. However, for all kind of purposes here, there might be collisions that are not really great examples of collisions that have mitigated forces, but we're just kind of ignoring those external forces to make it a little simpler. So we have an example of two cars that are colliding, right? And we've got car A and car B. And we are using kilograms as our mass, as I mentioned before, and we are using meters per second as our velocity. Now, weirdly, the units for momentum are just kilograms meter per second. So momentum, which I'm going to use as, they always like I use a lowercase p for momentum. I honestly don't remember why. I think it's M is used for mass, P, maybe it's a Greek letter. I don't know, you guys. I'm not really good with remembering why the units go with the certain letters. But the units here are kilograms and then times meters per second, okay? Or a kilogram meter per second. Not a very fancy unit, not like with force where we use newtons or anything like that. It's just pretty standard multiplication of units. So we got our first car, and I'll write the stuff with car A in blue. Car A's mass has a mass of 1,500 kilograms. And the velocity is 50 meters per second. So car A is actually moving. Car B is stationary, not moving at all, right? You'll have some examples later on where they're both moving. So it is really important to note the direction of movement as well, because if there's two different directions of movement, one of the velocities will be positive and one of the velocities will be negative. Because remember that velocity is a vector, so that means that it has a direction associated with it. So we can calculate the momentum of car A. Okay, so car A has a momentum of mass times velocity. I'm going to put a little sub A here to remind us this is for car A, okay? So that subscript just tells us which one. And we've got our momentum of car A. So 1,500 meters per second times 50. Oh, I'm sorry. Where's my eraser? Okay, maybe I'll choose white. This should be kilograms. That wasn't my bad. Kilograms times 50 meters per second is equal to my handy dandy calculator. If you guys don't have one of these already, I would suggest that you get the TI-30. So we have 1,500 times 50, and that is 75,000 kilogram meter per second, right? That's car A. So this is before it collides. Now, car B, it says, is unmoving. What do we know about the momentum of an unmoving car? It's 0, right? So we'll do this one in, let's do green. So car B is 0. So this is the total momentum before the collision. We're going to add these two together. So our total momentum prior to the collision is 75,000 kilogram meters per second. That's before the collision. This is all before the collision. Sorry about that. So if momentum is conserved in this collision, we would expect that after they collide, our total momentum will still be 75,000 kilogram meters per second. So let us go to the next slide and we will calculate it. After the collision, car A's velocity was 40 meters per second and car B's was 7.5 meters per second. So let's do car A again. Again, mass times velocity is equal to momentum, right? The mass didn't change. It's not like it got smaller, so it's still 1,500 kilograms. And it's now traveling at a velocity of 40 meters per second. So if we clear our calculators and we take 1,500 times 40, we get 60,000 kilogram meters per second. That's of car A. So when you're looking at conservation of momentum, you have to look at the total momentum before they hit and the total momentum after they hit. Okay, car B still has a mass of 2,000 grams. So we have 2,000 kilograms. And now its velocity is, what does it say? 7.5 meters per second. So it got nudged a little bit forward. So if I take 2,000 times 7.5, I get 15,000. So in order to figure out our total momentum, we add those two together, just like we did on the previous slide. And this time we get 75,000 kilogram meter per second. So before the collision, we have 75,000 kilogram meters per second, and after our collision, we get 75,000 kilogram meters per second. So when we look at kind of what we do for a general formula for conservation of momentum, our general formula is going to be mass of object 1 times the velocity of object 1 plus mass of object 2 times the velocity of object 2. This is before the collision, right? That is going to be equal to the mass of object 1 times the velocity of object 1 plus mass of 2 times velocity of 2. This is after the collision. What's going to change is going to be the velocities. The masses don't change, the velocities do, but you set up your equation this way to determine any of the variables in here. You can determine what is the velocity of an object after. If we know everything except for the velocity of object 2, we could determine the velocity of object 2. Okay, so then you're going to have some questions. What are some ways to eliminate as much outside force as possible? Think about how do we mitigate that, right? How can you calculate whether momentum was conserved before and after a collision? Just did that. You're going to do a little activity as well, and you're going to watch a short video. Have a few questions on that, the video. There's going to be a couple practice problems for you, so if you have questions on those, please let me know, but I do want you to try to practice them. And this is just kind of a fun example of how physics is not really observed in a lot of like science fiction movies or like Marvel movies and stuff like that. They can't because it wouldn't make sense. So you can kind of watch this about the superhero Dr. Dark, and there's some questions about it on the next slides as well. So that's all we have, you guys, for this lesson. If you have any questions, please let me know, of course. I'm always available, and have a great rest of your day.